Freshman. In today's video, I'm going to show you exponential growth in the real world. So let's review real quick from our last lesson. The equation for exponential growth and decay is y equals a times b to the power of x. If you remember from the last video, a represents the initial amount, and on the graph that represents your y-intercept. The b is your growth or decay factor. And remember, to get the factor, you have to do the following. If it's growth, you have to do 1 plus the rate. And remember, the rate has to be a decimal. If it's decay, you'll have to do 1 minus the rate. And of course, the rate is a decimal. The last two things, the x will always represent the time, and the y will represent the total amount. So now that you know this, let's apply it to a real world problem. So the very first one, the 2000 population of Jacksonville, Florida was 736,000 and was increasing at a rate of 1.49% each year. The very first step is to identify if it's exponential growth or decay. So you should notice the keyword increasing. That should tell you that the problem is exponential growth. So you know you're going to be adding 1 to 1 on this one. So part A, write the equation that represents the following situation. So exponential growth, the equation is y equals a times b to the power of x. And remember, to get the b, we're going to add the rate to 1. We're not going to subtract on this problem. So let's write the equation. So y equals, a represents the initial amount. So in the year 2000, the population was this much, 736,000. So that right there is your initial amount. Now we said it was a exponential growth, so it's going to be 1 plus. And if you remember from earlier, you have to put the rate right here, and that'll be to the power of x. So it said it's increasing at a rate of 1.49%. So to change that percent to a decimal, we have to move 2 units to the left, or in other words, divide by 100, and you get 0.0149. So this right here is your equation. You could go one step further and add inside the parenthesis, and you will get y equals 736, and then you'll get 1.0149 to the power of x. But either one is acceptable. So with this format, the growth factor is 1.0149, but with this format, you're able to see the rate, which is 0.0149. So either equation is acceptable. Part B, what will be the population in the year 2007? So if you go back to the problem, 736,000 was the population in the year 2000. So they were asking you for the population in the year 2007. So you have to ask yourself, how many years have gone by? And the answer is 7. And if you remember from the last slide, the x represents the time, so the lapse in time, and the y represents the total amount. So if we plug in an x value, if we plug in a time, we should be able to get the total. So if we plug it in, we get the following. By the way, notice that I made a mistake right here. The initial is 736,000, not 736. So 736,000. The growth factor is 1.0149, and they're asking us about the population 7 years later. So we're going to replace the x with a 7. Now to get the population 7 years later, you just plug this in the calculator. So 736,000, and it was 1.0149, I believe, to the power of 7. And the population is the following. So let's round to the nearest whole number, since population can be decimal. So it'll be A16,283. So the population in the year 2007 will be 816,283 people. Now, part C. In what year will the population be 918,812? So notice that we're trying to find the time or the year in problem in part C. So we write the equation, y equals 736,000, 1.0149 to the power of x. This right here is the total population. We're trying to find the time. In other words, they give us the y value and we are trying to find the x value. So substitute the y value. Now, in Algebra 1, you should only learn how to solve a linear quadratic equation, but not an exponential. You learn this in Algebra 2. But you do know a technique on the calculator. So of course, if you had a TI Nspire, you would do NSolve. But since we don't, let's go ahead and use our graph or our table. So go ahead and head on to Desmos. We're going to graph the left side in Y1. We're going to graph the right side under Y2. So we're going to make two graphs. And from the lesson from last week, you should know how this graph is going to look. We have a exponential growth because the b is bigger than 1. So you know the graph's going to look like this. Crossing the y at 736,000. And if you graph 918,000, it's going to be a horizontal line. So our solution is going to be the point of intersection between these two lines. So let's go ahead and graph it on the calculator so we can get our solution. So let's graph the left side and the right side of the equation, and then we'll look at the table. So y equals 736,000, 1.0149 to the power of x. So here's our first graph, and of course we can't see it because our screen is too small. And the second side was 918,812. So we've graphed the left side and the right side. So let's go ahead and find our point of intersection between the two graphs. So I'm zooming out. As you can see, that's our exponential growth. So that's my first equation. Now I'm trying to find the horizontal line, which will be at 918,000. So here it is. Here's the intersection between the two graphs. So let's zoom in and find the x value, which will be our time. Let me keep zooming in. So just click on it and it should pop up. So here's the point of intersection. So notice that the x value is 15 and the y value is 918,892. So let's talk about this. From our problem, we said that x will always represent the time and the y is the total. So on the graph, the x value was 15 and the y value was 918,812. So let me write that down. Our point of intersection was 15, 918,812. So let's talk about what this means. So remember, this is the x value, here's the y value. So 15 years later, the population will be 918,812. Now, the answer is not 15 here, because remember, it's talking about the year. And what year will the population be that amount? The initial year was 2000. And 15 years later, it'll be 918,000. So what you have to do is you have to add the two. 2000 plus 15 is 2015. So the answer to part C is 2015. Now, another way you could have gotten the solution is by doing the table. So I'm going to click on the first equation we typed in. I'm going to hit the little settings, this right here, this little tool, and you're going to hit the table right here. So I wish we would be able to plug in, y values, but we're not allowed to plug in y values. You're only allowed to plug in x values on this calculator. So if you look at the y values here, the y values are going up. So the y value should increase and reach 918,000. So I'm gonna pick random x values. So 5 years later, we're at 792,000. I'm gonna keep increasing the value. 10 years later, I'm at 853. So as you can see, we're getting closer. So I'm gonna keep increasing it. 14 years later, I'm at 905,000. So I feel like I have to go one more year. Of course, I already know the answer. And yes, if we round that up, we do get the number in question. So 918,812. So that's another way you could get the solution there, if you don't want to use the point of intersection, which is the easy way. So let's talk about example 2. So Omar bought a Lexus for 75,000 in the year 2005. The value depreciates 15% per year. So the keyword here is depreciates. Depreciates means to go down. That should tell you that you have an exponential decay problem. And it depreciates at 15% per year. So part A, write an equation that represents the value of the car. So y equals a times b to the power of x. So let's write the equation. Y equals a represents the initial amount. So the initial value of the car was 75,000. Now you said it was depreciate, so exponential decay. So we're going to do 1 minus the rate. So our rate, it's going down 15% per year. So remember, the rate has to be a decimal. So let's move that 2 units to the left. So remember, if you have 15%, if it's a whole number, the decimal is at the end, and we have to move 2 units to the left. 1, 2, and we get 0.15. Okay, so remember, you can do a little bit of simplification and you get y equals 75,000. 1 minus 0.15 is 0.85 to the power of x. And as you can see, here is our decay factor. It's less than 1, so it should be a decay problem, and it is. Now, part B. What will be the value of the car in the year 2008? So remember, this right here represents a x value, a time. So let's find the difference in years. The value of the initial car was 2005, and it's asking us about the value of the car 3 years later. So we're going to substitute 3 for x. And let's get our answer there. Let me clear all this out. So 75,000 was the initial. The decay factor is 0.85 because we did 1 minus 0.15. And then we're asking about the value of the car 3 years later. So that is 46,000, and it's round to the nearest whole number. So it's the nearest dollar. So it's going to be $46,059. How much was that? 49.59. So the value of the car 3 years later will be $46,059. So as you can see, it went down by a lot. Now part C. What will be the worth? No, when will the car be worth $14,765.60? So this right here is the total amount, so that represents your y value. So keep in mind that you're trying to find the time. So it'll be 14,765.60. So we're trying to find the x, the time. So once again, you do not know how to solve exponential equations, so we're going to use our calculator, our graph. So I'm going to go ahead and graph it. So y equals, it was 75,000.85 to the power of x. And the value was 14,765.60. Forgot to put y equals in front of it. Now I have both graphs, so I'm going to zoom out and find the intersection of the two. Let me try to... Here it is. So as you can see, the purple line is exponential decay. It's going down. Here's the intersection between the two. And that is 10 years later. So after 10 years, that will be the cost of the car. Because the x value, still remember, the x represents time. So x equals 10, but remember, it's asking you for the year. So the initial value of the car was $75,000 in the year 2005, but 10 years later, that leaves you at 2015. Go ahead and try the following. Pause the video and answer the question, then come back. The population of Smallville in the year 1890 was 6,250. Assume the population increased at a rate of 2.75 per year. Question is, estimate the population in the year 1940. So very first thing, the keyword here is increased. So you have an exponential growth. So let's write the equation, very first step. Y equals a times b to the power of x. So y equals a is the initial amount. The population was 6,250. Keyword was increase, so we have an exponential growth. So 1 plus the rate. It increased at a rate of 2.75% per year. So 2.75%, so divide by 100 or move 2 places to the left, fill that in with 0. So our rate is 0.0275. So let's leave this one like this. I don't want to go back and use the calculator for that. To add those, well, here, we'll need a calculator for this. Y equals 6,250, 1.0275 to the power of x. So here's the equation. Now let's answer the question. Estimate the population in the year 1940. Now the initial population was in the year 1890. So we have to find the population 50 years later. In other words, the x value is 50. So y equals 6,250, 1.0275 to the power of 50. Put that in the calculator, that will be your solution. So 6,250 1.0275 and we said it was 50 years later. So we round this, let me make sure my math is right. 0.0275. Won't make that much of a difference. Yes, it will, but here it is. So the population, if we round to the nearest whole number, it'll be 24,265. So the population of Smallville 50 years later will be 24,265 people. Go ahead and try the following. Pause the video and then come back. A 2-bedroom house in Nashville is worth $110,000 in the year 1999. It appreciates at 2.5% per year. So the keyword here is appreciates. Appreciate means the value goes up. So we have a exponential growth problem. So part A, what will be the cost of the house in the year 2005? Very first thing we have to do is write the equation. So y equals a times b to the power of x. So y equals the value of a is the initial amount. It's growth, so we're going to do 1 plus the rate. So it's 2.5%. Don't forget to move 2 units to the left and you get 0.025. It's asking about the population in the year 2005. So the initial year was 1999. So of course that is 6 years later if you subtract the two numbers. So the x value will be 6. So put that in the calculator and that'll be your final answer. One plus 0.025, and it's let me see if that's right, to the power of 6. So we round that to the nearest whole number. It is 127,566. 127,566. So the value of the house 6 years later went up to 127,566. Part B, when will it be worth $200,000? So again, on this one, that's the total amount. This right here is the Y. You're trying to find the X or the time. I mean, we could add those two and we get 1.025 to the power of X. So end solve, since you don't have end solve, let's graph left, graph right. Let me actually close this so we can go back to a, yeah, perfect. So 200,000. Don't forget to put Y equals in the front. That's our first graph, and then the second one is our equation. And then when we added that, we got 1.025 to the power of X. And again, I forgot Y equals, but on this one it doesn't matter. So let's find the point of intersection. So there's your exponential growth equation. Now let's look for the 200,000. 200,000. The point of intersection is this right here. So it is approximately 24 years later. So I just round that to 24. So X equals 24 years later. So when will it be 200? Well, technically it won't be 200,000 in the year 24. So let's round that up to 25 years later. Because at 24, it'll be less than 200,000. So now you have to add 25 to 1999. And you get 2024 after you add the two. So that was the end of the lesson. So go ahead and like, comment, and subscribe.